remember to drop that, just inconvenience. Suppose you've got a sequence, a series I should say, like this, and you want to test it using the alternating series test. Technically speaking, shouldn't there be a -1 to the end there, or it's not alternating? So glad I remembered. What do you need to prove? Well, you need to prove first that it's decreasing, and secondly that its limit is equal to 0. And if those are true, then this guy will converge. And as an added little benefit, let's suppose you used S5 to estimate it. You know, S5 just means add and subtract the first 5 terms. If you use S5 plus or minus the next term is an interval.
Took the words right out of my mouth.
Let's say you get 1.2. If the sixth term is 0.1.
You've been frozen since you wrote interval.
Oh, we are having one of those days, are we? Okay, has it came back yet? Okay, so at least you verbally heard me. Now you can see what I was saying.
No, we couldn't verbally hear you either. Your voice cut out as well.
Is anything working apart from you lot? Okay, from
the timing.
It's like the lag is deliberately trolling him.
It is not good. I don't know what to do. Whoever is using 20 gig bandwidth, will you stop doing it? Okay, let's. As long as your head is moving and I can't see anything, I will assume that you can hear me. Okay. Alternating series, if you can prove it's decreasing and you can prove that its limit is 0, then you have convergence. If you can prove to me that the limit is not 0, then you have divergence. If you want to estimate what a series adds up to, because we remember a series is a single value, right? So we'll assume that you've proved that it converges. If you want to know what it adds up to, you could decide just to add the first 5 terms. It's called the partial sum S5. The error or tolerance on that is the 6th term. So I'll give you an example. If you take that guy from n equals 1 to infinity, can you just trust me that you can prove he's decreasing and its limit is 0 so it converges? And let's suppose I would like to know an estimate of it using just the 5 terms. Well, if I use the 5 terms, I'd find S5. In this particular case, you're going to get -1 plus a half, take away a third, add a quarter, take away 1/5. Be a little bit hopefully I'm hitting all the right buttons here. We'll find out in a minute. The answer that I have got right now is -0.783. Well, it is to a certain amount of accuracy. Now, since I used S5, the tolerance or the error is the value of A6. And A6 in this series is 1/6. So you could basically say that, where is he? This guy here adds up to a number, negative 0.783, give or take 0.1667. So you can actually, although you can't actually find the exact value of many of these sums, for an alternating series, it's not too difficult to find at least an interval where you can guarantee that the answer lies. Now, if you wanted to get this interval to become smaller, in other words, you want this tolerance or error to become smaller, don't you just use more terms? You find S20 or S5 million. Nice thing is that can't you plug these into a computer? It's a very simple program. You could probably write it without 5 lines of code. Can you get it to do S a million and just do a for I equals 1 to a million loop or something, and off you go. So it's very, we do know what they add up to. At least we know what they add up to, any accuracy that you'd like. You can also use it for this question. How many terms do you need to add, I guess combine, to get your answer correct to, oh, I know, let's say 4 decimal places. So imagine you were doing this, you've proved it converges, and you'd like to know how many terms do I need to add up so that the answer I get is correct, meaning it's accurate to the real value, to 4 decimal places. Well, isn't AN just 1 over n? If you want 4 decimal places, you're basically talking that guy. Remember, if you want to round off, you have to go to the next place and stick in a 5, because 5 rounds up and 5 round down. So in other words, you're looking at 5 times 10 to the negative 5. So you just solve this problem. Well, doesn't that make n 1 over 5 times 10 to the negative 5? And since I got my calculator handy here, 1 divided by 0.1234, and the answer is, yikes. You'd need 20,000 terms. Actually, just to be safe, you need 20,001. So the alternating series is a relatively straightforward test. Prove that the thing's decreasing. Prove that the limit is 0. If you can do that, it will definitely converge. What will it converge to? Well, you can at least estimate it by adding some terms together. And the more terms you add, obviously, the more accurate your answer is going to be. And we even have a way of telling how many terms you need to add. So if you want to know an answer to 12 decimal places, can you imagine you just basically do 1 over 5 times 10 to the negative 13, add on an extra place for the rounding off reasons, and you're good to go. Agreed? Any questions about that? None that I can see. Okay. Well, let's just pick some. Let's see if I can pick something interesting. Right. Pretty interesting alternating series. First thing I would do is convert it to its real valued equivalent, which is that, because that's the guy that we can prove that it's decreasing with, right? Now you take this fella, you find its derivative. You might want to call this guy the natural log of x to the power of -1 and do it as a chain rule. You multiply by the power, you reduce the power by 1, and then you find the derivative of log x. And if you make all that look pretty, you get that. Now I just need to prove that this mess here, this thing here, is negative. And I only really need to prove it for values of x like 1 or 2 or 3. So I'm not going to pick 1, won't that cause some issues maybe with the fact that 0's in the bottom. But let's suppose I just say 2. You're allowed to wiggle the start number. Would you agree that log x, oh let's be safe, 3, right? Would you agree log x is positive when you reach 3? Would you agree when you square it, it's still positive? Would you agree it's on the bottom, it's still positive? Isn't -1 over a positive thing negative? I'm really doing that in my brain. Right, I'm not really doing any algebra. That's it, negative. We're good. Now, the second part of the process is that we need to show that this guy has a limit of 0. Well, how about brute force? Would you agree that the natural log of infinity is still infinity, and that 1 over infinity is 0? So out of the two boxes that you always seem to get in these questions, one says converge, and the other says diverge. Wouldn't you fill in that one? Are we okay, Edward? You're looking puzzled, or have you gone and frozen? Not, you're moving. You're good. You're getting me all worried now. Oh, I got a thumbs up. Good. I like thumbs ups. I'm going to move you lot over here for a minute. Yeah. I did get a letter, now that I'm thinking about it, it was an email, from Xfinity, who told me that I had used up my bandwidth or whatever, and that they were going to charge me money. But they're such nice people, they weren't going to do it this month, but if I do it again next month, they were going to charge me. And it was something ridiculous, like $10 for every gig over my limit, up to a maximum of $100. So you lot are costing me money. Do you feel guilty? Because I'm trying to make you feel guilty.
It's college's fault.
Yeah. I'll probably.
That's okay. We
So
found
I
out when we moved here, we had internet, and I didn't realize that. I think we have Wave, and I didn't realize it wasn't automatically unlimited because the internet we had in Georgia was just unlimited.
Okay.
And so we only stream. Like, we don't have cable, and I have 4 kids, and they all, well, 3 of them have devices, and so we got our first bill, and it was like ridiculous. It was insane, and they were like,
Right.
you could save a bunch if you just pay this extra $20 for unlimited.
Oh, like
So
they
we did
couldn't
that.
have sent you a little email when you hit your limit just telling you that? They waited till you got a big bill?
Yeah, but when I
Buggers.
called, and I called them, and I said, well, I'm not gonna pay that. No one told me. I was like, and they're like, oh no, it's fine. We'll waive it, and then you could just pay this $20 fee to get it unlimited. And then we ended up switching and having to upgrade to the gig internet anyway, because when the kids got out of school in March, because that's the only way more than one of us can be on a device, or like, because we stream all our television, so it's the only way we can get it all on at once.
I think I may have to do that. I don't know what one I'm on right now. I know it costs $80 or $90, so what one does that sound like? I use Xfinity, so I don't know what I've got. But I'll probably, yeah, I think I'm going to have to upgrade my internet or something so I don't get this weird thing
Yeah, it
happening.
varies so wildly, not only by ISP, but specifically by where you live. Like 6 months ago, I was living in Port Townsend. Now I'm living in Silverdale. But Wave was my ISP in both places, but the rates and speed rates offered were just completely different. The tiers were completely just as if you might as well be living in a different country different.
Yeah. Gotcha. Okay, let's show you another one. How about this one? Right, we got to look at convergence stroke divergence of this guy. There are two things to do. Isn't one of them prove it's decreasing? And the second one is prove that the limit equals 0. Actually, it's better to look at the limit first and prove the decreasing second. And this question gives you a good reason for that. Let's look at it. If I just leave it as ends, although I could turn it into its equivalent real valued function, would it be fair to say that it's pretty obvious that this answer, whoops, wrong way around, that this answer has a limit of 2/3? Agreed? 2/3 leading coefficients. Right. So doesn't that mean it diverges? End of story. Do I even need to bother spending time differentiating some really ugly polynomial over some equally ugly? Nope. You just go straight for diverges. So the alternating series test does tell you both. The diverging ones almost exclusively are going to happen with the limit not being 0. I'm trying to think in my head of an example of a diverging alternating series where the limit is 0 and this thing increases. And my brain can't come up with one because I think the logic would have to be like this. If you imagine this is 0 and this represents the individual members of the set, right? So you've got a guy here. What's meant to happen is something like this for a converger, right? Right? They decrease and they go to 0. That's what the ENs would look like if you plotted them. I'm trying to think, is there a way that you can be increasing and go 0? Well, yeah, that's true. But for that to happen, the ENs can't be positive, so that's not allowed. Okay, it's probably not true, but here goes. If the limit's not 0, it diverges, and you're never going to get a divergent series that has a limit of 0. So all alternating series will fail if their limit is not 0, right? That's pretty much what my brain's telling me. Okay, let's see if we can find some guys to work on. How about this fella? Oops. Well, you can imagine what our first job's going to be is to actually figure out in sigma notation who he is. So let's see if we can make that happen. N equals 1 to infinity. Now it's either -1 to the n or -1 to the n plus 1. The first term, that's going to be the first term. That's going to be add the second. That's going to be take away the third. Oh, wait a minute. There we go. And fourth one. So it has to go negative plus or plus negative. In this case, I'm making it that guy. If you want the first term to be negative, will you use n or n plus 1?
Plus 1.
Okay, let's try it. -1 to the 1 plus 1, -1 squared. Oh, that's +1. So it has to be n. But you see, it's not hard. Can't you just pick one? If it works, use it. If it doesn't, it's the other one. Right? It's not that, you know, it's not that onerous a job. So we got this part done. Now, it looks like I need a formula for AN. I'm pretty happy about 1 on the top. I'm pretty happy that it's a square root of something on the bottom. But now I have to figure a way of 1 gets you 3, 2 gets you 4, 3 gets you 5, and 4 gets you 6. So now I have to figure out what would n get you. There's a pattern here.
And
1
plus
gets
2.
you. That's the guy I'm looking for. Now, if if you excuse me for a second, I will just mute you all. We don't want to hear someone's personal conversation. Okay, my thing's going. Am I breaking up here because something's not right? We good? Huh. Okay. Okay, I've lost you. Where the heck are you? Okay, so here we go. Right. Basically, don't we have to prove that is decreasing and its limit is 0? I'm not going to, pretty much because I think it's pretty standard. Would you agree we'd do that, guy? Wouldn't this be able to prove 0 just by brute force? Isn't it going to be 1 over infinity and that gets you 0? This guy's going to be messy, but you're going to have to call him x plus 2 to the negative a half and then differentiate it and show it's negative. And you know, you're done. Let's try this fella. Gut feeling, is that guy going to converge or diverge?
Converge.
Agreed. It's got a good sign to it. This isn't a proof, so you're not allowed to do it, but this is a kind of rule of thumb. Would you agree that this thing basically behaves like 1 over the square root of n? And don't we already know that 1 over the square root of n converges? In fact, doesn't 1 over any power of n converge? Right, so 1 over n to the half converges when it's part of an alternating series. If it's on its own, it actually diverges, right? Because 1 over the square root of n would diverge if everybody was positive. But when you're an alternating series, 1 over any power of n will get you 0 because each term gets a little bit smaller than the last and you get this kind of ziggy-zag thing where it disappears. So I'm going to look at the algebra issues involved in differentiating and proving something has a negative derivative. If I want to differentiate this guy, I very often have to rewrite it in a form that's going to make it play better with the formula that we use. Do you recognize this as a quotient rule for differentiation? So the derivative is going to be f dash g take away f of g dashed over g of squared. I'm picking this ugly guy so that in the future today I can just say trust me, you can differentiate it and prove it's negative rather than spending 10 minutes doing every single one of them, because some of them take you forever. Okay, differentiate the top, you get 1. Leave the bottom alone, you get that. Take away, leave the top alone, and now we got a really weird chain rule. We got 1/2 x cubed plus x to the power of -1/2 times the derivative, which in this case is 3x squared plus 1, all over that guy squared. Well, at least a square root, when you square it, stops being a square root. So what I have right now for my derivative is I have an x cubed plus x to the power of 1/2. Take away 1/2 x, 3x squared plus 1, x cubed plus x to the -1/2, all over an x cubed plus x. Now, as much as you might like to, you aren't allowed to go, yeah, that's obviously less than 0. Because there's no way in the world that is obviously less than 0. So we are going to have to do what I call style points, which basically means factor the heck out of this thing. Well, there's not an awful lot that this term shares with this big ugly term. But there is one thing they share. Don't they share an x cubed plus x? This guy has got a 1/2 power of it. This guy has a -1/2 power on it. So we are going to pull out x cubed plus x, and the power that we're going to pull out as a common factor is the -1/2. Because when you do common factors, isn't the rule the smaller of the two is the common factor? Right? When you do x cubed and x to the 6, isn't x cubed the common factor, right? The smaller of the two. Now, that gets used up. So here I'm going to have -1/2 x, 3x squared plus 1. And here we got a problem. If you take a -1/2 power away from this guy, don't you essentially add it? So you get a 1/2 plus a 1/2, which gets you x cubed plus x. Now check it out. X cubed plus x to the power of 1 times x cubed plus x to the power of -1/2. Don't you add the 1 and -1/2 together? You got your guy. It works. Which means that I'm now left with this guy comes downstairs. And this stuff here is basically what we've got left. Which now gets me this guy. Check that out. Good. That gets you that. X, take away that guy, gets me that. Yep, looks good. Now I'm going to pull out 1/2 x, and that leaves me with -x squared plus 1 over x cubed plus x 3/2. Right, so that's the neatest version, right? The style point version of this derivative. Now, let's assume that x is greater than or equal to 2, just to be safe. Would you agree a 1/2 x is positive if x is greater than or equal to 2? Positive. Would you agree that this horrible mess is positive, and if you raise it to the power of 3/2, it is still positive? What does -x squared plus 1 look like when x is greater than or equal to 2? Isn't -x squared plus 1 always going to be negative? What does a combination that looks like this give you? I have now proved that it's decreasing. So the act of proving something is decreasing can be quite complicated. Proving that the limit is 0 is typically a lot easier. Now, all you're going to get is a little button that says converge, diverge. Most of the questions look like that. And you are going to go converge. And no, you are not, even although I have no way of enforcing this, I'm going to say it like your mum anyway. You are not allowed to just pick one of these two at random and find out it's wrong and pick the other one. And I'll repeat it again. You are going to get, guaranteed, questions from this chapter. And in those questions, if I don't see the proof, I don't care if this is right, you're getting nothing. Because all it means is that you guessed. And you don't get 20 points for guessing. That's not the way this works. Now, I can understand that when you're doing your homework, you may choose, because there's time issues, of not doing every single one of them, because it's just quite onerous. I think you should definitely do the limit part. That's not that onerous, and it's good practice. And you might want to choose, you know, to maybe drop one or two on this vein. But if you've got the time, it is definitely worth it, because maybe the one that you decided to skip is the one that I pick in the test, and that would not be a good idea.
Professor,
Yeah,
you plan on making the final the same amount of questions as the midterm, but just like,
20?
yeah.
Yes,
Okay.
that's my goal. I might not be able to keep to it, but that's my goal. My goal is also to find better questions. I didn't like the midterm. So I'm going to go hunting for other people from other places who've created. I'm not trying to catch you. I just want questions that aren't like, well, I could go and look up question 8 in my homework and it's the same guy. They've just changed the 4 to a 5. I don't want to do that.
Yeah.
I'm not testing you if I do that. So, you know, I'll go hunting for things. That's what my goal is anyway. About 20.
Okay.
Okay. Right, I'm looking at another fella here. Let's see this one. What do you think? Converges, diverges? Is that e to the 1 over n's a problem, isn't it? Is it going to get there? Is it not going to get there? Is it going to decrease, for instance? That's the problem. Let's just do the limit part. Because if that limit's not 1 and not 0, won't it diverge? In which case we're kind of finished. You agree that there's really only one method that's going to work with this particular expression. And it's called orbital. I'll put it down here. I think I need more room. Well, the bottom's easy. Is that the answer, or should I have done more? Differentiate the bottom, differentiate the top. Okay. Shouldn't I finish with the derivative of 1 over x, or 1 over n in this case, which ends up being that guy? To which you should say, that's not meant to happen. So what's wrong? The what's wrong is, it's not L'Hopital. It's actually brute force. Right, let's do 1 over infinity. Isn't 1 over infinity 0? So won't this be e to the 0 over infinity? Isn't e to the 0 1? Isn't this 1 over infinity? Which means, isn't the answer 0? Can you remember when you did L'Hopital? And I hope if you got me, you certainly would have heard it because I rant on a lot about this. L'Hopital is really good, but don't use it when you shouldn't, because things will go weird. Don't use L'Hopital when there's square roots. Do you know what happens when you differentiate square roots? Don't you get even uglier square roots? L'Hopital's designed to take ugly guys and make them nicer so you can find their limit. If you take an ugly guy and you make it even uglier, you're going to go nowhere. And would you agree ugly guy is even uglier now? Side issue, but show you. This isn't infinity, but it gets across, I think, the same idea. Suppose I wanted to find the limit as x tends to 1 of this fraction. Now, actually, I don't need L'Hopital for this fraction. Can't I just go 1 plus 1, 1 squared plus 1, the answer is 1. Great. Suppose I use L'Hopital on it. Won't the derivative be 1 and on the bottom it's 2x? Can I plug in 1 now? Yes. Do you see the L'Hopital when you use it when you shouldn't? Might give you an answer, and the answer is wrong. Why did that happen? L'Hopital only works in what's called indeterminate form situations. 0 over zeros, infinities over infinities. That's where it was designed. That was its niche market. Don't use it for 0 over 1s, because the answer should be 0, right? Don't use it for situations like 1 over infinity, which is what happened here, right? These, we know the answers. In fact, don't use it for infinity over 1 because the answer is infinite, right? So when you're looking at a question and you're about to say, I wonder what technique I'm going to use here, that one almost kind of screamed out L'Hopital. Didn't it look like a L'Hopital question? But in fact, it wasn't. Try a very quick version of brute force. Brute force doesn't take a lot of time. Let's give an example. Right, here's brute force. E to the infinity over infinity. Isn't that infinity over infinity? Yes, use L'Hopital. This one, sine of infinity. Don't know what you are. Over infinity. Do you know I can still tell you the limit is 0? I don't know what the sine of infinity is, but don't I know that the sine of anybody is a number between 1 and -1? So pick a number. A half. Isn't a half over infinity going to get you 0? It probably would have been better to put a square there just to get the positive answers all the time. What would this guy get you if you did brute force on it? You get infinity? Yeah. So, little issue. Next fella. I think, I think I've got 2 more of these I want to do, and then I want to show you that little bit at the end where you try and estimate the value of it, and that's pretty much this done. So this is one of the two guys that we've got at the end. Okay, guys like this are brute force or L'Hopital, right? And it's always a good idea to try brute force in your head. Would you agree the log of infinity is infinity? And would you agree 5 infinities is infinity? Isn't this indeterminate form? L'Hopital is cool. So it's going to be the limit as n tends to infinity of 1 over n and 5. And I would probably make that look a little bit prettier. Bingo. Pretty cool, pretty smooth. Limit is 0. Oh, I think I'll break my rule here. Prove it's decreasing, right? Let's do that now, because that's the second part of the coin, the second side. If you do its derivative, you're going to have to do a quotient rule. So it's going to be 1 over x times g, take away f of x. Let's try that again. F dash g, take away f of g dashed over g squared. That's better. 1 over x times this guy, take away log x times this guy, all over 5x squared. So what do I have? I have 5, take away 5 log x, all over 5x squared. Okay, let's assume that x is, I don't know, 4, just to be safe. Provided x is greater than or equal to 4. Would you agree that bottom term is going to be positive because everything in the universe squared is positive, at least every real number is? Would you agree that as long as x is 4 or more, won't this term be negative because this guy will beat that guy? And the combination is negative. So I've now proved it's decreasing. So when you prove it's decreasing, get the derivative and then just find out individually what all the pieces are made up. So can you imagine a question where that bit is negative, this bit is positive, that bit is negative, and that bit there is negative, right? So it's made up of lots of pieces. Won't that combination generate a negative answer, and therefore it's decreasing? Any questions, or are we good? Last chance. We're double thumbs good. Almost at the end of this. There's one with factorial. I'm trying to find it, aren't I? Oh, didn't take me long. Okay. What the heck is that doing in an alternating series exercise? The cosine of n pi over n squared. The cosine of n pi over n squared. What the heck is that doing? Well, do you know it is an alternating series? If you plug 1 in, you get the cosine of pi. If you plug 2 in, you get the cosine of 2 pi. You plug 3 in, you get 3 pi. Well, do you know cosine of 1, 2, and 3 pi are negative, positive, negative. So what you get is negative, positive, negative. In other words, it's that guy. So that's essentially a disguised alternating series test. That one's guaranteed to converge, and you can go and prove it in your own time. So last piece of this puzzle, and then we can move on to a new section. We're going to look at estimating the value of an alternating series. Okay. N equals 1 to infinity, negative 1 to the n over n squared. Can we just assume that I've proved it converges? Because it really does. It's not that hard to converge. But let's suppose that I want to get the answer to this correct to, say, 3 decimal places. Now, if you're thinking about 3 decimal places, whatever the answer is, you want to be plus or minus 0.0005. Not 0.001. So why is 3 decimal places this thing and not that thing? Well, remember, it's rounding off to 3 decimal places. Now, when you round off to 3 decimal places, don't you look at the 4th decimal place? And if it's 5 or more, right, you go up, and if it's less than 5, you go down. That's what that is doing. So, for this question, right, I'm going to be looking for when is this fella, right, equal to that guy, which is the same as when is this fella equal to that guy. So I'm just going to go to my calculator and do a 1 divided by 0. Let's try that again. I'm going to do a 1 divided by 0.0005, and I get 2000. And then in this particular case, I'll take the square root of 2000. So square root of 2000. And I get the answer, 44.7. Okay. How are we going to work this? You can't do 44.7 terms, right? That doesn't make sense. Right? You can do 44, you could do 45, right? Something like that. Do you think you should round off to the nearest number every time? Well, if you did that, would you agree 45 would be the correct number of terms? So if you want to find what this converges to, and you want to know what it is to 3 decimal places, you will find S of 45. Don't worry, you don't get asked to do it, because that would take you a long time by hand. But can you imagine that's how you would do it if you said to a computer, or calculator, or whatever, you know, do this for me. What are you going to do in that situation?
Probably use 45
Good answer. Why? It's right. Why?
to ensure that we're actually being accurate.
Yeah. You want to be safe, right? So if you did 44 here, could you imagine that you don't quite get the accuracy you want? It could be just a little bit out and it doesn't round off exactly to 3 decimal places. So the rule of the game is always round up. Right? Always round up. Cool. Now that one I could do algebraically, right? It wasn't too hard to take the formula, make it equal to this guy and then solve. But not all guys are equal. Can you just trust me that that guy converges? We're not going to prove it because it's too difficult, and we'll prove it later when we do a thing called the ratio test. But it converges, right? And I would like to know what it converges to 4 decimal places. So we start off with that guy, and we make him equal to that guy, right? If you prefer, that fella, right? You cannot algebraically solve this puzzle, right? You can't, do some weird logs to both sides or something. It just won't work. What you got to do is basically brute force. So here goes. You're going to guess. So I don't want to guess, because if I guess, I'll probably get the right answer on the first guess. And I want to show you how you do it when it doesn't work the first guess. So give me a number. A guess.
Six.
That's a pretty healthy guess. Okay, so I'm now going to go to my calculator, and I am going to find what 5 to the 6 over 6 factorial is. So it shouldn't be too hard. 5 to the power of 6 divided by 6. Does anybody know where the factorial is? It is on your calculator. It's hidden inside a menu somewhere. Do you know where it is? Here we go. Hit the math button. Scroll over to the end, and it's choice number 4. Okay, go. Round there. What happened there? 5, 5, 5, 5, 5. Ooh. I think we have a long way to go. Just checking this. Actually, I better check this converges. Five, 5, 5, 5. I'm just imagining the sequence. 1, 2, 3, 4. Ooh. We could be here all day with that one. This one, same problem. This one will converge really quickly. So I'm going to stick that guy in the bottom. Otherwise, I think we'd be guessing a long time with the other one, because if that's 21, I could, God, it might be 8,322 rocks, and I don't want to spend forever doing that one. And the questions you get are typically less than 10 anyway. So 1 divided by, put a bracket around it, 5 to the power of 6, multiplied by 6 factorial. One divided by bracket, 5 to the power of 6 times 6 factorial. And okay, we got an answer. 8 times 10 to the negative 8. Aren't we looking for an answer that's in this range? So does that means really that 6 terms is more accurate than we want? Can you see it's well into the 7th decimal place, this fella? Right, so since it's a guessing game, if that's too much, don't you pick a smaller number like 3, and hopefully that's too little, and then you've only got 2 more shots. So n equals 3. Let's see what we get here. If I do second entry, do you know you can just bring up the last calculation? And then I can just replace that guy with a 3 and replace that guy with a 3, and it saves me having to hit too many buttons. Right, this is 3. Oh. Okay, it's not 3 then. Where are we off to? 4 or 5? You have a 50-50 chance of guessing. Any guesses?
4.
Good the choices, any? Okay, I'll just do the second entry trick. 5 to the power of 4 times 4 factorial. Oh, so darn close. Don't we want that? Haven't we got just a little bit too much? So if it ain't 4, oh, wait a minute. I'm going to have to pick 4 because I don't have any more room. Right, it's either 3 or 4, and 3 is not going to make it, and 4 is going to. So after that work, a little bit of guessing. That's pretty powerful. This particular one gets within 4 decimal places of whatever the real answer is, and you only need to do 4 terms to get it. It's pretty impressive. The one that I had way over here, I have no idea how long that's going to take. I'll give you an example of a bad one. Do you know if you did 1 over n and you wanted to do this guy? Do you know you would need, I believe, it's either 200 or 20,000 terms. You don't want to guess on that one, but actually you don't need to. But can you imagine that the guessing technique really is only restricted to within 10, right? Which is what the answers are. You're also going to have to, unfortunately, find out what the answer is. So since we decided 4 is going to work for that, can you imagine going up here and putting in 1, 2, 3, and 4? And what you would get would be the first fella would look like, n equals 1, this fella. And then the second guy would look like this fella. Then the third one would be this fella. And I don't have room for the fourth one. You'd have to do that ugly calculation. And then you could write down negative 0.1234 or whatever it was. So at the end, you're going to have to do some button pressing. And that's, as far as I'm concerned, we are good for alternating series. Is there anything you want me to go over? Or are we cool? We good? Right, good nods. Right. So let me kick out of this thing for a while, and we'll give you a head start on next one. I'm going to put the next section homework up, but it's not going to be due on Sunday. It's going to be due a week on Sunday. But if you want to get a head start so you've got less homework to do the following week, by all means do so. Right. So what you're going to be seeing in a few seconds from now is our next section, and it's called absolute convergence, and then it has a couple of tests in it. So let me close this. Open that. We got anyone in the chat I need to know? Okay. People are. Okay, let's look at page. Here we go. All right. We're going to look at what's called absolute convergence, and then not today, but next week we'll look at 2 more tests. They're called the ratio test, and they call it the root test, but I call it the nth root test. It's the same test. So what you got here, maybe I should make this a bit bigger. Can you imagine that you're given just any old series? It could be an alternating series, it could be any series. And can you imagine that if you picked any universal series in the world, you could have situations where some terms are positive and some terms are negative, right? Not all series are made up of just positive things added. An alternating series just happens to have a pattern where they go plus and minus. But can you imagine in other worlds, you might get 10 positives, then 3 negatives, then a positive, and 4 negatives, right? And all sorts of zinging up and down. So what the absolute convergence series, what the absolute convergence says is that if you have a series that converges and you make everybody positive and it still converges, then it's called absolutely convergent. So the original series has to converge. That's the first hurdle. Then you say, suppose everybody was made positive, right, and you added them up, would it still converge? And if the answer is yes, then you call that guy absolutely convergent. So here is an example of one. They make a meal of it, but here goes. Alternating series are very often the ones that you do absolute convergent tests on. I guess it's a test. Can you imagine -1 over n squared? It converges. Can we just say it? Yeah, I know it's going to. We've seen ones like it. That's what it looks like, right? If you make everybody positive, do you see that's what it looks like? Do you know that one also converges? So that makes this then absolutely convergent. Now, how does that converge? Well, do you recognize a P series, P equals 2? That's why I know it converges. Now, here's a guy that we've been playing with. You remember the alternating, the harmonic series, in this case, the alternating harmonic series, right? It's one of the family. Oops, come back. 1 take away a half plus a third take away a quarter. That guy converges. We proved that yesterday, I think. If you make everybody positive, don't you get the harmonic series? And doesn't that diverge? So can you see there's an example of a series where if you left it alone, it would converge. But if you made everybody positive, the new series diverges. Now, when that situation happens, it's called conditionally convergent. So there's now 2 types of series out there. There's the absolutely convergent. They absolutely converge no matter what you do to the buggers. Not only can you make them all positive, do you know you can make them all negative and it'll converge? Do you know you can alternate them, make plus, minus, it'll still converge? Now, they'll converge to different things. You can imagine if you added a whole load of things together, it wouldn't be the same number as the first guy, take away the second, add the third, take away the fourth, right? But absolute convergent are basically indestructible. Once they are absolutely convergent, you can pretty much do anything that you wanted to it and it's still going to work. For instance, do you know you could take an absolutely convergent test and double all the numbers? It would still converge. You could take an absolutely convergent series and make it an alternating series. It'll still converge. Right. Conditionally convergence, they are very dangerous, and that's why we even looked at them. So let me show you a really mind-blowingly not intuitive property. You know this guy? I'm doing the one that starts with the positive. Right. That guy converges, right? You can prove that with the alternating series test. Can you also say that it's, when you make everybody positive, it diverges? So this guy is conditionally convergent. So let's show you this weird thing. And trust me, this does not intuitively make sense. I am going to take this fella. forever. And I'm going to play about with what its sum is. Right. Can we say that this is equal to S, right? Just for argument's sake. Right. Agreed? Now, if I split this into two distinct groups, would you agree that whole package is the same fellow? I've just put all the positives together, then at the end of the universe, I'll tag on all the negatives. Now that gives me this piece, and if I pull out negative a half, we get this piece. What does 1 plus a half plus a third plus a quarter to eternity get you? Isn't that infinite? So this guy is made up of all these guys, take away half of infinity. Do you think that's going to end well? What do you think this is going to add up to? All the pluses then? Don't they have to add up to some version of infinity to cancel out this kind of infinity? Does infinities take away infinities end well? The problem with conditionally convergent series is it depends on the order that you decide to add the infinite terms. The way I've written this one down, if you do it, it will home in on the number log 2. But if I decide just to rearrange them just a little bit, you know, like this. You see, all I'm doing is like shuffling the cards. See if you did this series, which is basically made up from the same guys, but the order that I've been doing them has changed. That guy also converges, but he doesn't converge to log 2. He converges to some other number. And if you decide to shuffle them differently, I can make it converge to any number you want if I was clever enough to do the math. Which means conditionally convergent series only converge to the number that you would get if you left the thing alone. If you start mucking about with them, you can make them converge to other things. You can even make them diverge. Can you see how dangerous it would be to work with a conditionally convergent series if you didn't realize that you were in very thin ice? That if you had somehow put the data together in a slightly different order, it would home in a totally different number. Absolutely conditional series don't have that problem. You can rearrange them any way you like, and they always converge, and they always converge to the same answer. It's not obvious, and maybe it's still not obvious, but hopefully it's a little bit clearer, that conditionally convergent series can turn into anything. And so we don't like them. Don't you like the certainty of knowing that it converges and it converges to a half? No, it converges. Well, if you write it that way, it's going to be a half. But if I jumble it up, it can make it converge to 2. And if I do it another way, I can make it go infinite on you. I mean, you're on very rocky ground there if you do any kind of decent math with that. I would not want to use a conditionally convergent series on any calculation. Couldn't I have got the series the wrong order? Or I was adding it in a way that I shouldn't have for the situation I'm trying to solve. Are we good? Right. So let's I think I've got tons of time. Let's do some examples of finding conditionally convergent. absolutely convergent or divergent series, because you can stick in some of them with it. Right. This one I'm picking because it's pretty easy to do, and it's in the textbook. And I'm talking through this, but you got to imagine we did it properly. Would it be pretty obvious to tell that that alternating series converges if you did all the stuff? Would it be even more obvious, because that is a P series, that this converges? So that makes this guy absolutely convergent. How about this fella? You're just going to trust me on this. This guy does converge by the alternating series test. And can you imagine it's 1 over infinity, so its limit is 0. A little bit less obvious, but can you trust me that it is negative, so it decreases, right? What about 1 over the natural log of n? Well, that diverges. Let me prove it to you. Do you know that that guy is bigger than that guy? You know, 10, 1/10, 1 over log 10. Isn't 1 over log 10 a bigger number than 1 over 10? Aren't you bigger than a P series that diverges? This is a comparison test, but it diverges. So that makes this fella conditionally convergent. This third fella, what do you think is going to come out of that one? Any ideas? What about this series? Is that convergent? Is that convergent? What's the limit of that fraction? I'm trying desperately not to just tell you the answer, because I tell you the answer, you'll say okay, and then you'll forget it because you never thought it through. What is that guy?
1.
And what does that tell you about that series then?
That it converges.
What's the limit got to
no.
be? Right,
And it's got to be 0.
right. So what does it tell you then?
It diverges.
That's what you need to do. So you can look at that and you can say, oh yeah, okay, I believe him. But if I write down another one and you just stare at it and you say, I don't know how to do it, then you've really not got anything. So you got to think these guys through. So that would be a divergent, right? Well, we don't have 2 flavors of divergent. We don't have an absolutely divergent and a conditional divergent. We just have, you ain't working. I don't care what you do to them, it's divergent. So here are your 3 worlds. Absolutely convergent, conditionally convergent, and finally divergent. And I am now going to spend a few moments just taking a quick screen grab.